Hello everyone, welcome back to our deep learning course. In last video, we tried to discuss about the introduction to deep learning and about the artificial neural networks. So during that time, we tried to see about some of the problem of the training in deep learning, like the problems like overfitting and underfitting. So today we'll continue about the how to avoid these overfitting problems. So our today class, maybe actually the first one, we try to see about avoiding overfitting problems, and then we'll try to see about the different deep learning models like the convolutional neural networks and recurrent neural networks like the LSTM and GRU. So first, let's start from how we can avoid the overfitting problems, especially in deep learning algorithms. Overfitting will be the main problem. So let's see about this one. So the first technique that help us to avoid overfitting problem is regularization. So this regularization, which is like a mechanism or a text that constraint our optimization problems that try to discourage complex models. So just the reason why we need to use this one is to improve the generalization of our models on the unseen data or unseen data, or which is we call it new test data. So the one technique, actually there are different regularization mechanisms that help us to improve the performance of the models, especially on the test data. So this regularization, which is like that helps us to prevent the overfitting problems, and which is help us to control the performance of an algorithm, that help us to reduce the test errors, but not on the training error. So mostly or more focus on when we use regularization, that's like because when we say that overfitting, just like we can say that the training error is less but the test error is high. So our focus is mainly that helps us to reduce the test error. So because of that one, this regularization technique that helps us to reduce the test errors. So for instance, if we want to decay for regression problems like this one, so the function, which is like the mean square error of the training plus the weight of this one, so just the cost function to be minimized on the trainings, and then there is also this control factor of the preference that we try to assign the smaller weights on this one. So just this is like that try to fit the training data, and we try to small the weights on there. So let's see, for instance, how the regularization will be trained over parameterized networks. So actually, when we say that the first one is underfitting, this is a structure that shows that the difference between how we can say that underfitting and overfitting problems. So from this one, when you say that underfitting, actually, just like this is at the beginning of the training, the model still does not capture the most important parameters of the data set. So which means like the model cannot have the awareness about like the data. And then at the middle of this one, we call it the ideal fitness around this one, which means like in this area, the model have a good experience about the data sets, which means that the generalization performance becomes to better. And this is, we call it overfitting problems. So these overfitting problems means that it showed that the training error is becomes small and the validation error is high. So this regularization technique will be just like try to minimize the problems of this validation error, or we call it testing error, which is the same. So by checking like different parameters, we can try to avoid this one. So this overfitting, which is like the training loss, is low, validation loss is high. We already saw the technique that we try to use for this one is the first one. For instance, you have enough data. So if the size of the data is too small, so the model is like because of have high capacity, so it try to capture every parameter of the data, and that means it creates memorizing every data, but just like it forgets about the test data. So that's just so the data should be like the most important parameter. You need to have enough or large amount of data to training in the deep learning models. The other one is actually just like it can be possible to use like data augmentation. This is the data generation techniques just to increase the data sets, and then we can arrange also the learning rate tunings, because actually learning rate means like we can try to determine the learning speed of the model, so we can arrange the value on the learning rate and also the other parameters, so we can adjust that parameters in order to regulate the overfitting problems of the models, deep learning models. So the one is regularization and also the model complexity. Like this is in general some of the techniques that we try to use for solving the overfitting problems. So this one issue that, for instance, the other technique that we try to use for the solving the overfitting problem is early stopping. Actually, we try to see this one also in the next one. So let's focus on the regularization. So actually, there are two type of regularization. That's called ridge regularization, which is called L2 regularization, or there is also L1 regularization to reduce the overfitting problems. Then, for instance, when you see these diagrams, this is actually with like polynomials with different degrees. For instance, this way the degree m is equal to 9. And then there is also learning rate here. So plot polynomials with degree m is equal to 9, which is like fitted with this data point. So as shown in this one actually, which is like a better one. And the other one, actually, there is a weak regularization also here, just like the regularization performance or value. So this one, which is the gamma 10 to the power of minus 8, is the regularization value. So we can assign or we can give the regularization value, and that is just help us to regulate the overfitting problems. And the right one, actually, just it's a strong regularization. For instance, the value is 10 to the power of 3, which is like we call it a strong regularization. So when we try to develop the models, we can just assign the regularization values in the model, and that helps us to just regulate the overfitting problem. Because here, for instance, because of the regularization value is too strong, it's like still now actually does not try to solve the problem. So as much as possible, you need to just give like the regularization value is too small, and that is the best one. So rather than giving the strong regularization, giving a small regularization is better than strong regularization. So from this diagram also, we can see that the left side will have just better performance than the right one. Uh, so this one actually also like within the different like regularizations, and also with like different degree, like line degree. So the regularization when like is like excessive, and also medium, and then the maximum, which is like overfitting. So just like we can try to assign or adjust these regularization parameters, and then we can get the best values. So for instance, from this one also, it can be shown that the left side of the figure, it showed that low regularization and parameters can become very large. So that, and the right one is to select the model with small generalization errors on the validation sets. So for this one, so we can just, for instance, here there are different regularization weights. So around this one, actually, you see that the performances, they become like more better and better. So we need to assign. This one is how like the regularization value affects on the overfitting problem. So this is with different regularization value, and this is with the different errors. So when the regularization value is increasing, the error is also increasing. So we need to manage. So mostly actually, just like increasing too high the regularization value still just leads overfitting problems. So you need to adjust these values. So in general, actually, there are two regularization types: L1 regularization and L2 regularization. Just actually, both of them is like a type of regularization, but mostly actually, maybe to avoid overfitting problems, L2 regularization is better than maybe L1 regularization, because in this case, when all features should contribute, and the regularization will be just like, or that just try to encourage small weights, and that helps us to shrink weights, but does not seem to just like zero. Instead, this one just all add up solid values of the weights instead of that one. So, and also that makes exactly with zero. So because of that one, just like different value, but you can try also like by using L1 regularization or L2 regularization. So just the difference between these two regularization is already put in this table. So you can try to read from this one. So this is, for instance, an example that showed that how we can just define the regularization on the model development. For instance, this is the sample model that developed using the Python. So this is a model, so a neural network model. So the model will be here, a neural network model, which is model.sequential. And then this is a model.dense, which is the activation function is relo. And this is just the shape of the training data. So the training data always will be explained here. And then kernel regularization. So regularizer, the value is here 0.001. So input layer with L2 regularization, for instance, here, this is L2. L2, this one defined that the type of the regularization will be L2. So you can change this value. For instance, right now I assign 0.001, but by changing this value, you can just like monitor the regularization. So this will be applied in the first layer of the module, and also then we can apply the other one, and then also here in the second layer, so we can apply also regularization, L2 regularization, and the value will be just like hidden layer with L2 regularization also in the second layer. So when you add this one, it's not a must. So regularization is not like the must parameter that we need to add in the module, but this regularization is only added if your module have a problem of overfitting. Unless you can just remove this one. If your module has no regularization overfitting problems, this one just kernel regularizer is equal to regularizer dot L2 is like, it's not a must parameter in the deep learning model. But when you see that the graph between the validation and the training graph, if there is overfitting problems, you can just add like this type of parameter, and then by changing this value, you can monitor, you can regulate the overfitting problem. So you can add just like with each layers, like for instance this case, so the first layer, and we can add dropouts, and the second layers, and this is just the last layer, which is, we call it the output layer. So the first one is input layer, and then this one just dropout layer, and then the second one, which is hidden layers, and this one is the output layer. So in the output layer, which because this one is, we can use softmax activation function, as we discussed already in the previous classes. We say that softmax activation function mostly that used in the output layers for multi-class classification purposes. So softmax mostly that uses for in the output layers. Then the other one actually, which is like similar with the previous one. For instance, here compile the modules, define like the other one, and then the next one. So we will try to see step by step. So the first technique that we try to use for avoiding overfitting problem will be regularization. I mean regularization techniques will be like the one technique. The other techniques to avoid the overfitting problems, we call it dropout. So dropout means randomly dropping out network connections with a fixed probability during training, like shown. For instance, this is the original network that's shown on the left side. In the right side, just randomly some connection will be dropping. For instance, here you see that the connection between this one is dropped. The connection between this one and this one will be dropped. So that drop means some of the connection between the layers will be disconnected, and that helps us to also monitor the overfitting problem. So that's just dropout means this one. From some layer of the connection will be automatically drop out when we apply actually this one. And let's say how we can apply. So this is just, for instance, an example that showed that how like the training is a sample without dropout and with dropout looks like. The performance will be improved when we apply dropout. So dropout is the one technique that helps us to monitor the overfitting problems. Without overfit, you see that just like the performance will be is less or just high error, but just like when we apply dropout, the performance will be improved and shows like this one. And then how we can apply dropout in the deep learning courses. This one, for instance, is just like similar with the previous one. For instance, here regularization is added, and next this one, our module name is just NN module or neural network module. NN module dot dropout. So the module name dot dropout, and then you can assign any value 0.3 here. Mostly actually we need to give like a small value 0 point and fractional, and you can give actually any values, and then you can apply dropout within each layer. This one, for instance, in the next to the input layer, and also we can apply, for instance, dropout in the hidden layers, and then just like we can apply like a number of dropouts within each layer. So here we can apply dropout in the input layers, and then we can apply dropout also in the this one. So 0.3 means dropout layer, which is 30% of the neurons will be dropped from the connection. That's why. So if we just like 0.5, 50% of the layers will be dropout. So by assigning this value, you can just try to monitor the overfitting problems, as well as also you can improve the just like performance of the model. So dropout will be the second technique that helps us to solve the overfitting problems. The third technique to avoid overfitting problem will be early stopping. So early stopping is just stop training before we have chance to overfit. That means early stopping means the model is just try to iterate. So just like during the training, there is an iteration. So when just like a small error is achieved, the model is try to stop on that steps. And then instead of just continue to check the other one, the model will be stopped when the best solution or the best performance will be achieved. That is, we call it early stopping. Let's see, for instance, this one. So the loss will be here, for instance, just like it starts to iterate and becomes down this. So around this one, if the performance around here is the best one, it will be just start to stop here, early stopping. So just like this, you see, so just like try every step. So you see that in this case, for instance, maybe it will be stop around here. Either this area, it showed that there is overfitting problem because the gap between the testing error and the training error will be very high here. So if the gap between the two is high, which means like there is overfitting problem, so the early stopping condition that helps us to just stop the training around here. So no need of waiting around here, just it will be early stop around this step. That means around here maybe the performance will be better, so it will be stop on that conditions. So you see that, for instance, stop training around here. So the condition around here is better, so the model is automatically stop around here when the minimum value or the minimum error will be achieved. That condition we call it early stopping. So this one we call it underfitting. The around here is overfitting, and but this line will be, we call it like the optimal model. So just automatically checking that which step or at which iteration point will be the minimum value, the minimum error is achieved, or at which epoch or iteration the model achieved the best performance. By checking that one will be stopped on that step. So how we can apply the early stopping. So this is, for instance, the code that shows that how we can apply early stopping. So we can define early stopping callback like this one. So we can say early stopping, then monitor value loss. So what is the condition that try to check in order to stop early is validation loss. So just the model it try to check, or as a criteria, as a method to check that or to stop the condition. As a criteria, it uses a validation loss as a criteria to monitor the error. So by using validation loss, the model it try to stop early. So the patterns actually just like try to wait like 5 and then restore best weights, which is like try to capture this one. Then this one is just like early stopping is defined here. Then during the training, we need to just try to call it this early stopping. So this is a training, for instance, simple NN history, simple NN model dot fit. So simple NN model dot fit. Actually, simple NN model, because here during compilation of the model, we say that simple NN model dot compile. So here the model name is just like we can say that simple NN model. So here just simple NN model dot fit xtrain, ytrain, epoch, batch size, validation, and here callback z equal to early stopping, which means the model try to check these conditions. So by using validation loss during the training, it will be try to use validation loss as early stopping mechanism. So by using like this type of ways, we can try to stop the condition when like the small or the better performance is achieved. That's just the one technique that we try to solve the overfitting problems. The other one is actually we need to try to just adjust different parameter or hyperparameters. So just in order to determine this model's complexity, there are different parameters. We need to just adjust that parameter. Maybe epoch, maybe hidden layer, maybe neurons, maybe like optimizers, activation function, batch size. All these parameters have just an impact on the performance of the model. So you need to just rearrange or reshuffle that one to improve the performance of the model. So I think this is just related to parameters, so we can just avoid. The other one is the splitting data. The way of splitting the data will be also just having the effect. So in order to avoid overfitting problems, maybe I think the arrangement or the data that we have to train the model should be huge data or enough data. So we need to split the data. Maybe just the training data should be better than or higher than the test data. So training data, like for instance, 80% of the data should be for training for the model, and 20% of the data is for testing the model. So we can try to use like this type of ways, or also for splitting the data. The one technique to avoid this overfitting problem is we call it cross validation. So this cross validation that allows to estimate the generalization errors based on training examples alone. Like for instance, this is a k-fold cross validation, the one technique that helps us to just split the data as a training and testing data. So this is the one hyperparameter tuning which is common in the size of training data. Is small, especially if the data set is small, it is better to use k-fold cross validation to test the or as a training and test data. So this is also, it's a better and less noisy estimate of the model performance by averaging the results across several folds. So this is actually the, for instance, let's say 10-fold cross validation. Like this one is a training data, training set like this. So in first iteration, we can use the 10. So let's say, for instance, we already split into 10 folds, or the data will be split into 10 folds. So split the training data into 10 equal folds. So we can split into 10 equal folds, and then like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, like this. Then the second step will be first use of the fold 1 to 9 for training and fold 10 for validation or for testing. So which means like in the first iteration, 1, 2, 3, 4, 5, 6, 7, 8, 9. This one is for training. The rest will be for testing. In the second step, this one will be for training, and also this one will be for training, and this one is for testing. So every data should be used as a training at one time and then a test at another time. That is just a technique. That means we can train the model by using the whole data, as well as also we can test the model by using the whole data. That is just a technique. We call it cross validation. So that is just repeat by using fold 9 of the validation, fold 8, fold 7, fold 10 just. So the average, the result over 10 runs. So we can 10 runs for reporting purpose, which is the average result will be, that helps us to determine this one. So once the best hyperparameter is determined, we can evaluate the model on the test data. So this is also the one technique that helps us to just like determine or reduce the overfitting. Unless sometimes maybe when we split the data by using like 50-50 or 60-40 or 80-20, because the data is randomly selected, sometimes maybe that's just maybe similar data will be selected for training and the other one for testing. And so maybe they will not just understand every data clearly. Because of that, the overfitting will be, they happen. So cross validation is the one technique also. So this is, for instance, a sample code that how we can apply the k-fold cross validation. So k is equal to 5. K is equal to 5 means like now we can create 5 folds. So which means like the data will be split into equal into 5 folds. So k-fold number of split which be k. So the value of the key is here 5. So shuffle is true, random state actually bad. So just like we can determine or we can apply this key fold into the training data. So just that's the technique for applying this one. And then we can apply also the normalization techniques. So about normalization, just like try to normalize the mean and the variance static of the layers, and also the activation function, batch size, and all this, just like we can try to normalize, and this will be improve the performance of the models. So this batch normalization, just like try to accelerate learning is by making the optimization landscape much smoother, much smoother. And this one just helps us to impact the regularizers and it affect network capacity in the generalization of the model. We need to try to see that what are the design issues in the ANN or artificial neural networks. The first one is number of nodes in the input layer, maybe just like one input node per binary or continuous attribute. So we need to determine which one is the best number of nodes. So sometimes maybe if just we make it a number of nodes or it's like if not compatible, sometimes it leads to overfitting or underfitting problem. So we need to just assign the best number of nodes for depends on the data size actually. So the number of nodes in the output layer, number of hidden layer and nodes per layer, initial weight and bias, this will have just some issues, the design issues. So that is why sometimes actually maybe you can design or you can create like or you can use 3 layers, and also like the number of the neurons will be just like different, the number of hidden layers will be different. It depends on the problems as well as the data sets. So you need to be just always try by your own data set. So it will be different from data set to data set or from problem to problem. So it's not always like the same. So this is actually some of the deep learning trends. We need to use this one actually, just like the most common deep learning trends. So this is a class discussion questions. Maybe just like you can try to answer these questions. Or for instance, the first question, what is a neural network? And then you just try to briefly explain the concept of the layers in neural network. What is the input layer, hidden layer, and the output layer? Just try to figure out these questions, and this helps us to just understand about what is the neural network. The second question will be just why the neural network requires large amount of data to train. And then how does this training improve the model ability to make the accurate predictions? So just try to answer these questions and it will be help us to just understand in detail about the neural networks. Okay, so this is just all about the class artificial neural networks. So just we try to see about from the introduction part about neural networks and different activation functions and about overfitting problems, bias and variance, and then how we can use different techniques to avoid these overfitting problems. Just we try to summarize this one. In this section, we try to complete this one. So in the next section, we try to see about the convolutional neural networks or which is like the most popular deep learning algorithm. So we'll try to continue about that one.